All right, so how's everyone feeling out there? Okay, last warning. We got a lot to do. I'm in serious mode. So, today's lesson is on engines. Physicists would call them heat engines. You know, regularly they're just called engines. The whole premise is you're taking heat and you're using it somehow to do work. Here we have a diagram of a complicated engine, yes? And you might notice, whoa, what happened here? You might notice, folks, this is the diagram we've been, working on over here. And, here we have our container. Yes, and we have our piston that goes up and down. Well, maybe you could spot it in the big diagram, yes? But here we have the cylinder, but it's upside down. And then this thing right here, that's the piston. So with our diagram over here, this piston goes up and down this way. Over here, it goes down and up that way. I was looking for animations showing how this piston works in action. Let's take a quick look what I found. Whoopsie. Okay. All right. So, basically, it's a four-step process. It's called a four-stroke engine. And you can see the upside-down cylinder. And ultimately, it's making this guy right here spin. It's making that shaft spin. The processes go through kind of quickly. Let's see if we could start it over again. All right, here we go. Watch carefully. Ready? They show it broken down. All right, they're just warming you up. Watch. Okay, step one, the induction stroke. All the gasoline and the oxygen is brought in. Step two, the compression stroke. The piston squeezes that stuff, so it's higher pressure. Step three, spark plug goes off. Boom, explosion. Power stroke. Pushes that piston down really hard. So hard it whips all the way around, and now this valve opens up, and it's the exhaustion stroke, and it pushes the exhaust out the other side. So the piston goes up and down twice for each cycle. Now, once this bar here is spinning, that's got to be somehow or another transferred to your tires. So let's go back. There's your engine, yes? Well, the engine turns that crank, and there it is right there. It's called the drive shaft. So when that piston is going up and down, it's turning that bottom thing, which is turning that thing right there. You can see it turning, yes? And finally, the drive shaft to the wheels. That drive shaft is turning. Yes? That's it right here. That's it turning right there. Yes? Well, when it turns that way, it makes this other guy rotate this way due to that gear right there. And then once this shaft here starts spinning, ultimately, that's that guy right there. That spins the tires. So basically, how do the tires, how do they get forced to turn? Well, it all boils back to, this cylinder right here. And of course, there's not just one of them. There's usually like 4 or 6 or 8. So sometimes you say, oh, I have a V8. I have an 8-cylinder car. So there's 8 of these things working together as a big team. Or maybe it's a 4-cylinder. So today's lesson is all about the thermal processes for a heat engine and what those thermal processes look like on a pressure volume graph. We're not going to be mapping out a pressure volume graph for a 4-stroke engine. We're going to be looking at a very, very simple engine, but hopefully it'll give us a feel for what the pressure volume graph is supposed to look like. I'm not sure because I revamped them last night again. I compressed some things down. We have 2 more to go. This one and another one on efficiencies of engines. So, do you know how the engine we just saw, it goes through a complete cycle and then it starts over again and goes through the same thing over again, yes? Well, on a PV graph, ladies and gentlemen, it basically is going to look something like whoa. You have the gas at some point, some condition, yes? And basically, the condition is going to change, and the piston might move, and maybe it's going to go like this, up to, another point. Maybe that's point B. And then conditions are going to change again, and it's going to go through another thermal process to another point, maybe point C, and then it's going to go through another thermal process to another point, point D. But if it's an engine, it always ends up going back to the original point. And then the whole cycle starts over again. So if you ever see a problem with a PV graph where you have a closed loop like that, it's either going to be an engine or it's going to be a refrigerator. If it's an engine, it's going to start at a point, go through a whole bunch of different processes, end up back at that point, and basically, it's going to take heat energy and turn it into work. So for the whole process of of an engine, the whole cycle, your Q is going to be positive. When I say the whole cycle, I mean for the whole shebang thing, starting out at point A, and you go through the whole thing, and you end up at point A. When you go through the whole cycle, the total heat for the whole cycle has to be positive. And remember, that means that heat is being added into the system. And for the whole cycle, you want the gas to do the work. The gas is going to push up that piston and ultimately turn the shaft that turns the tire that makes you go down the road. But you got to be careful on that, because if the gas is doing the work and is lifting up the piston, what's going to be the value of the work for the whole cycle if it represents an engine? Negative. It's going to be negative. So W is going to be a negative. It turns out that if you look at the closed loop on a PV graph, if it's going clockwise, it's an engine. Now, a refrigerator, on the other hand, or an air conditioner, wants to take heat out of the system. And when you're taking the heat out, that doesn't happen naturally. So it takes work from the surroundings. Work is done to remove heat. So, since the heat is going to be removed, if you look at a whole cycle, from A to B, B to C, C to D, D to A, from A all the way back to A again, when all is said and done, what has to be the deal with the heat? Positive or negative? It's negative because you're trying to take the heat out. But this requires work. Now the gas is not going to be doing the work. The work has to be done by some outside mechanism. So the work in this case is positive. And as a shortcut, if you looked at the PV graph and you saw a closed loop, and if it was going counterclockwise, you're like, oh, that's representing a refrigerator. So let's take a look at a very basic engine to help you get a feel for what's going on. If you haven't been following me, by the end of the lesson, go back and read through this stuff again, and it might make more sense. Because now we're going to break it down and look at it step by step. To kind of speed the process along, I made these handouts so that you could just fill in the diagrams as we go along. Well, the free response questions are those midterm review questions.
Oh, are you about to?
Yes. Yeah. Sure, let's get those legs back on. Yes. Yeah, I would definitely eventually get these in your notebook if you want to just tape them in or. Okay, so the side that has the 3 diagrams.
So these are right side up, it's actually
What's that?
Shouldn't it be up, like, flip the other way?
Yeah, it doesn't really matter which way. This particular engine is, we're going to keep the cylinders the way we've been looking at them. Okay? But you're absolutely right. It's flipped from the standard. Yeah. So, basically, ladies and gentlemen, we're going to try to make our simple little cylinder with a gas in it an engine. And basically, it's not going to be a 4-stroke engine. It's going to be a 2-stroke engine. The piston's going to go up, and it's going to go down, and then we want the process to start all over again. And when that piston goes up and down, this crankshaft thing right here, that gets pushed up, but it's connected to a wheel, and the wheel is kind of like spinning on that little point right there. And basically, when the piston thingy here rises up, this beam right here is going to push up on the wheel, and basically the wheel is going to start to turn this way. Yes? But I want to draw that on this diagram. Sorry about that. Because for step number 1, what we're going to do is we're going to hold the wheel still, and we're just going to add the heat to the gas. Now I know this is not a realistic engine. This is just an engine for educational purposes to help us learn the process, yes? So imagine that we hold the wheel still. And if we hold the wheel still, that means the piston can't move. And we start off with an initial pressure, volume, temperature, number of moles, and we could plot that on our graph right here. There's the initial volume. Here's the initial pressure. We come along here. This point right here represents the initial condition of the gas, point A. Question. Question. So we have the gas, it's in its original condition with its original pressure, original temperature, original volume. We're holding the wheel still so the piston can't go up and down. And we're going to add heat, baby. That's right, because that's what an engine needs. It needs heat. So we're going to put a Bunsen burner underneath it. Here's the flames. Woo, woo, woo. And we are going to add heat, baby. And if we add heat, but we don't let the piston go up, we hold that piston still, what's going to end up happening to that gas on the inside? First of all, what kind of process are we going to be dealing with? Think about yesterday, we learned about those 4 structural processes. Steven, what kind of processes are we? What kind of process are we dealing with? Isochoric. Isochoric process. And what does an isochoric process look like, Eric? Do you remember on that PV graph? If it's constant volume,
But the pressure goes up, so it's like up, down.
that's what I'm talking about. So we can go ahead in our diagram here and we can draw an up arrow, straight up. And that's going to bring us to some second condition. The gas is going to be changed now. It's going to be a higher pressure, higher temperature, but the same volume because we held that piston still. You with me? Huh? Okay. So this is point B. So this is the process from A to B. And then we look at the next thermal process. And during the next thermal process, we're just going to let the wheel go. And when we let the wheel go, that heated up gas that has so much pressure is just going to like, whoo, push upward. So we can go to our next picture here. And basically, the piston is going to go from that lower state up to the higher state. And when it goes up there, the wheel is going to turn from like over here to over there. So we are at point B. We release the wheel, and the gas does some serious work. Yes? And it lifts that piston right on up, which turns the crank, which turns the wheel, and now you're just that much closer to Syosset High School. Yes? Okay? Now, let's look at the PV graph. If you let that wheel go, and the piston rises and turns the wheel, what's the new volume now? What's the deal with the volume? Krishma?
The volume increases.
The volume increases. So we're going to be like, here's the original volume. We're going to be, up here somewhere, yes? But at the same time, when there's that big increase in volume, guess what the pressure ends up doing? It decreases. Yes? Now, it's probably going to be a more complicated thermal process than what I'm showing here. But what I'm going to show here would be like a very good educational one to look at, yes? And basically, the gas goes from this point B up here to a point C down here, which happens to be straight across from point A. So this is our point C over here. And again, it probably wouldn't be linear, but to keep things simple, for learning's sake, we're just going to make it a linear thermal process from B to C. And the truth of the matter is, the heat would still be on there too. Yeah.
It always goes back to the initial pressure when you stay there.
Not necessarily. Only in this simple example that I'm using to teach you. Not necessarily at all. Okay? Now, finally, during the last phase, we want to get things back to the way they were at the beginning, yes? So what we're going to do, ladies and gentlemen, is we're going to remove the Bunsen burner, and we're going to surround the container with like bags of ice cubes. So this is in the next diagram. And during that next diagram, by taking the heat out, okay, basically the piston is going to drop down, and we're going to go from C back to A. And when you get back to A, you're going to have the same exact pressure, volume, temperature as you had to begin with, and the whole cycle starts over again. So this is from C to A. And basically, the whole graph ends up looking like that one shown in that last diagram. And you're like, oh, closed loop. Oh, clockwise. Oh, this must be showing the thermal processes for a heat engine. Now, a lot of times, you're going to have to fill out this chart over here on the right, and you're going to have to calculate the change in internal energy, the heat, and the work for each of the thermal processes. From A to B, from B to C, and from C to A. Sometimes you're asked to just fill out the chart like I did here and put in whether it's positive or negative. So I want to set you up for success here, folks. So let's just take a look at our big diagram here. You might want to sketch this back in your notes away. And let me remind you, for the 4 endpoints, if you can read the volume, and you can read the pressure, and usually the number of moles is given down below, yes? Well, if you can read the pressure and the volume, and you know the number of moles, what else can you calculate for each of the corner points? The temperature. So, as a little reminder to that, at each of the corner points, I'm just going to write, right there you could use PV equals nRT. And for this little corner point, you could use PV equals nRT. And for this little corner point right there, you could use PV equals nRT. And then for the thermal processes, as the gas is changing from one condition to another, what's very commonly used for calculations for a thermal process, for the red arrow calculation, yes, where you have one condition and another condition, well, you can use the ideal gas law for 2 states of a situation. Remember how that law looks? I think you guys call it the combination law, yes? Combinate. So basically, if you're going from one condition to another, you could use PV over T equals PV over T. You could use that for this red arrow, between B and C. So like if you want it, you could say in here, oh, that's going to be B, 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 and this is C, C, C. Likewise, from C to A, you could use the combination law, PV over T equals PV over T. And over here, you could use PV over T equals PV over T. And it might simplify for the various processes, it might reduce down. But in general, the red arrows, the thermal process, you can apply the combination gas law. Now, the other thing you can apply to each of the thermal processes. No, back to the corner points. Back to the corner points. You know how for those corner points you can apply the gas law? Well, if you know the temperature now because you did PV equals nRT, you can calculate the internal energy of each of the corner points. So for each of these corner points here, you could use U equals 3/2 nRT. And over here, if you know the temperature over there now, you could use U equals 3/2 nRT. And if you know the temperature now at this point, you could use U equals 3/2 equals nRT. All right, back to that chart. Okay, here we go. This is on the back of that handout that I gave you. It's on the back, yes? Or on the front, whichever you want to look at it. Yeah? Okay. Look. You got to remember, each red arrow, like from A to B, right here. From A to B. This red arrow right here. That thermal process. As it went from A to B. A to B. You were heating up, but you were holding the wheel still, yes? Well, you're going to have to calculate. You're going to have to calculate the change in internal energy, the amount of heat added, the amount of work done. But one thing to remember, folks, is that this formula right here, the first law of thermodynamics, applies to each row. So look, if you know what this is, and you know what this is, you can use this formula right here, add them together, now you know what this is. Or if you know what this is, and you know what this is, you can put it in the formula, and you can get the third. So anytime you have 2 out of the 3 on a row, you can figure out what the third one is. You with me, people? This is like a puzzle. It's like Sudoku. Is that what it's called? Okay. Now, let's go to the next thing you need to remember. Look. If you add up, see if you can follow me on this, people. Ready? If you add up the change in energy, internal energy, from A to B, and then you add the change from B to C, and then from C to A, well, if you add all those changes together, you end up getting the change from A all the way around to A again. So basically, with this chart, if you look at the columns, if you have this, and you have that, and you have that, well, if you add those 3 together and you add down, that's got to give you the total for that measurement. If you know the work done from A to B, and you know the work done from B to C, and you know the work done from C to A, you add those 3 together, that tells you the work done for the whole process, A to A. You with me, people? Okay. Now, last but not least, calculating the change in internal energy, that's pretty easy. We like calculating the change in internal energy. We could use this formula here, and we could calculate that change in internal energy. Just watch out for your signs. Check this out. Since delta T equals TF minus TI, you have to fill in the blank here. If TF is bigger than TI, then delta T, would that be positive or negative? If TF is bigger than TI? positive. And if delta T is positive, looking at the formula right above, what's the deal with delta U? It's also going to be positive. So now that we know the temperatures of those endpoints, we can so easily calculate the change in temperature. And if you know the change in temperature, you can come back here and figure out the change in internal energy. We like calculating delta U. Same thing with W. We like calculating W. We have two different ways of calculating W. We could use the formula, or we could calculate the area underneath the curve. But once again, you have to watch out for the sign, whether it's positive or negative. Take a look at the fill in the blank down here. Let's say that you have delta V equals VF minus VI. Well, if VF is bigger than VI, what would delta V be here? But you got to be careful now because of our notation. Remember, when delta V is positive, what is the work going to come out? Look at the formula. It's got that negative in it. Negative. Hold your horses. Let me make my final statement here. Two more statements. Okay. Number one. Q is hard to solve for. There are formulas where you can actually take Q equals MC delta T, and you can revamp it into this thing called Q equals NC, capital C, delta T. But it's a pain. What I suggest, and I haven't seen a problem yet that doesn't allow you to do this, always solve for delta U and W first, and then use the formula to work backwards to get your Q. The last thing that I wanted to say, if you start at a point, and that point has a temperature, and then you go through the whole process, 1, 2, 3, and you end up at that point, back at the same temperature, what's going to be your total change in temperature for the whole process? 0. So back on the chart right here, from A to A, delta U, if you add these 3 down, is always going to be 0. If it's a engine, and we talked about this at the beginning, Q is always going to be positive. The work done is always going to be negative. Now, if it's a refrigerator, it would be 0, negative, positive. You guys have been very patient. Now, finally, there's one more lesson. I'm going to teach it today after school, 2:30 to 3 o'clock. Anyone wants to come watch it live, you're more than welcome. Otherwise, please watch it tonight on the efficiency of these engines. Thank you. You guys have been wonderful.